Hello everyone and welcome to today's video lecture, which is on the gamma function. Specifically, we're going to derive the Hankel contour definition of the gamma function, the Hankel representation as it's sometimes called. And this is, in my opinion, the most beautiful representation of the gamma function that we've seen so far. It's certainly the most general. So that's what we're going to focus this video on. We are going to derive the Hankel contour representation of the gamma function. Okay, that purple letter there is the Greek capital gamma. And we're going to show just how general this definition is. We're going to show that this representation for the gamma function is actually valid for all complex numbers, except where we have poles at the negative integers, which we already know about. And we're going to do this through a technique called analytic continuation. So first I would like you to recall the following. The gamma function, as we originally defined it, it was originally conceptualized as a means of extending the idea of the concept of the factorial. And it was initially defined for all positive real numbers. And we wrote that gamma of x, where x is a positive real number, equals the real integral from infinity to 0 of the function t to the x minus 1 times e to the negative t dt. And that equals x minus 1 factorial wherever x is a positive integer. And the expression is also valid for all positive x, so it extends the factorial to the positive real line. We then showed that the gamma function can be extended to complex numbers that have a real part greater than 0 by writing the following, by basically just plugging in z in the place of x. So we'll write gamma of z equals the integral from infinity to 0 of the function t to the z minus 1 times e to the negative t dt. And this was valid, this expression was valid as long as the real part of z was positive, was greater than 0. So that expression is valid over the right half plane in the complex plane. But we then showed that by performing integration by parts on that expression for the gamma function, we could actually extend the definition of the gamma function. We could derive new formulas for gamma of z that were valid over increasingly large regions of the complex plane. And this was our first example of what we call analytic continuation. So just to illustrate what exactly I'm talking about, I'll draw a complex plane here. We'll label our coordinate axes x and I times y. And we saw that the gamma function, written in the integral form that I exhibited before, is valid whenever the real part of z is greater than 0. So I'm shading in this entire region. This is the region of the complex plane whose real part is greater than 0. And we wrote that gamma of z equals the integral from infinity to 0 of t to the z minus 1 times e to the negative t dt. We then showed that if you take that formula and integrate it by parts twice, you arrive at a new formula for gamma of z, which agrees with the old formula of gamma of z on the right half plane, but is now valid for every complex number whose real part is greater than negative 1. So I'm going to shade in that region here. This is the set of complex numbers with real part greater than negative 1. The formula also demonstrates that we have a pole at z equals 0 and z equals negative 1, and I've circled those points in yellow. So this new formula for gamma of z, which represents the analytic continuation of the gamma function, is gamma of z equals 1 over z times 1 over z plus 1 times the integral from infinity to 0 of t to the z plus 1 times e to the negative t dt. And we don't have to stop there. We can do another integration by parts on this expression. And when we do so, we continue the gamma function to an even larger region. we'll find that this expression is now convergent and valid for all complex z with real part greater than -2. So I'm shading in that region here. This is all z whose real part is greater than -2. And our formula for the gamma function is now gamma of z equals 1 over z times 1 over z plus 1 times 1 over z plus 2. I'm running out of space here, so I'll write the integral in the next line, times the integral from infinity to 0 of t to the z plus 2 times e to the -t dt. And so on. We can do this integration by parts as many times as we want to continue to push out the boundary of convergence for the gamma function on complex numbers. So by this process, we are able to extend the domain of convergence of the gamma function to larger and larger regions. In fact, we can extend the domain of convergence of the gamma function to the entire complex plane if we were to carry on these integration by parts infinitely. We would still have poles at 0, -1, -2, -3, and so on at 0 and all the negative integers. But that's one way to analytically continue the gamma function to the entire complex plane. And that's a neat trick. But the natural question arises, is there a formula for the gamma function that's valid for all z? In other words, is there a way to write the gamma function in such a way that we don't have to keep doing integration by parts to iteratively extend the domain of convergence of the gamma function? And the answer to that question is yes, there is. And one expression that's valid for all z is the Hankel representation, the Hankel contour representation, which is what we're going to derive in the remainder of this video. So that's the motivating idea behind this entire video, to represent the gamma function in a form that's valid for all complex numbers. And in order to do that, we're going to start by translating the gamma function, which up until now has been written as an integral on the real line. We're going to translate that from an integral on the real line to a contour integral in the complex plane, which is a more general form of the integral than what we've worked with so far. And I should just stop right here and say to anyone watching this video who's not familiar or comfortable with contour integration and complex analysis, there are tons of great videos on YouTube that explain how contour integration works, and I would refer you to them so that you can bring yourself up to speed for this video. It's not a very difficult or tricky concept to get a handle on. But let's compare the two concepts of integration of a real valued function and integration of a complex valued function. If we have a function of a real variable, in this case gamma of x, we would write that gamma of x equals the integral from infinity to 0 of the function t to the x minus 1 times e to the -t dt. And I can even graph that function, t to the x minus 1 times e to the -t, for some x. So that's my function there, y equals t to the x minus 1 times e to the -t. That's on the yt plane. And this integral, gamma of x, will just be the area under that curve whose particular shape will be determined by whatever my choice of x is. And of course here x is a positive real number. So gamma of x is just represented as the improper integral from infinity to 0, which is the area under this curve. It equals the integral from infinity to 0 of the function t to the x minus 1 times e to the -t dt. Now we saw that we could get a valid definition for complex z whose real part is greater than 0 if we just plug in z in place of x. So we're still doing an integration along the real line, but this is sort of an intermediate case because we're doing an integration along the real line, but we're situating that real line within the complex plane. Here's what I mean. I'm going to draw the complex plane, but I'm going to label my real line t and my imaginary axis I times t. And we'll write gamma of z equals the integral from infinity to 0 of the function t to the z minus 1 times e to the -t dt. And I'm integrating along the real line again here, even though I'm doing so within the complex plane. So, in fact, this is a contour integral where the contour is just the positive t axis. That's what I mean about this being a kind of intermediate case. We're not using the most general contour possible, we're using the positive t-axis for our contour of integration, which is what allows me to write gamma of z equals the integral from infinity to 0 of the function t to the z minus 1 times e to the negative t dt. So t is still a real variable here, and so the question would be, what if we allow t to be complex? So that brings us to our most general case, the case where we have f of z equals the contour integral c over some contour, which we'll discuss in this video at length. And instead of t, we'll use w representing a complex variable, to the power z minus 1 times e to the negative w dw. And again, w and z will both be complex numbers here. So that's the most general form of the gamma function that we're aiming towards. So again, I have a complex plane. I'll label my coordinates again t and I times t, but my contour here is not going to be confined to the real line t. My contour is off the real line. This isn't really what the contour is going to look like, this is just an example, but the point is the contour, which I've dashed to show that it's to be determined, is going to be off the real line. So that's our most general case, this contour integral. And we want to choose our contour of integration for our function w to the z minus 1 times e to the negative w in order to somehow get at a more general definition of the gamma function. So we want this integral over some contour c of w to the z minus 1 times e to the negative w dw to equal gamma of z. That's our goal. Now we're not going to get exactly that for the result, but that's what we're aiming for. So what should our contour look like? Well, it turns out that the contour of integration that we choose is to some extent influenced by the nature of the function that we're trying to integrate. And here's what I mean. I'll ask you to recall that the function w to the z, where both w and z are complex numbers, that this function has a branch point at w equals 0, where the function is actually undefined. And furthermore, the function has a branch cut originating at the point w equals 0, originating from this point. Now why is that? The reason for this is that the function w to the z, where w and z are both complex, is equal to e to the z times the natural log of w, and the natural log of w, the complex natural logarithm, is undefined for w equals 0. And to be single valued, the complex natural logarithm requires a branch cut. So if this is at all confusing to you, please see my earlier video on complex logarithms, branch points, and branch cuts. Well, these issues also affect the function that we're trying to integrate here. For starters, just take the function w to the z minus 1. This would equal e to the z minus 1 times natural log of w, the complex natural log, of course. And again, we have this branch point at w equals 0. It also affects the function w to the z minus 1 times e to the negative w, which is the function that we're trying to integrate here. Again, e to the negative w is well defined everywhere, so that's not causing any problems. But it's being multiplied by this function that does have a branch point that's undefined at w equals 0, and that has a branch cut. So these are hugely important considerations when we're doing this integration. If we want to do a contour integration in the complex plane for our function w to the z minus 1 times e to the negative w, our domain of integration looks like this. Here I'll draw our coordinate axes, and I'll label them x and I times y. And we have a branch point at the origin. That's our branch point. And now where are we going to put the branch cut? Well, this takes some thought. We have to put the branch cut somewhere so that we're limiting the variation of the argument of w between 0 and 2 pi. Well, it turns out that the best place to put the branch cut is just along the positive x-axis. So that's what I've done here. And then the question would be, fine, that's our domain of integration. What should our contour actually look like? Now remember that we want to derive a formula for gamma of z equals the contour integral over some contour to be determined of the function w to the z minus 1 times e to the negative w dw. Up until now, we've defined the gamma function in terms of an integral along the positive real line. But we can no longer do that because we put a branch cut there. We've made the function undefined on 0 and the positive real line. So how are we going to recover a definition for the gamma function having done that? Well, our strategy is going to be to draw a contour that's really, really close to the path of the original gamma function, a path of integration along the positive x-axis. And then we'll take the limit as our path of integration gets closer and closer and closer to our branch cut, so that in a sense, the gamma function itself becomes the limiting case for this more general contour integral. So let's draw the contour now. For my contour of integration, I'm going to draw a line parallel to the x-axis, parallel to the positive real line, but set off from it by some distance which I'll call epsilon. So I'm integrating in the complex plane parallel to the x-axis, but some distance away from it, which we'll call epsilon, and I'm starting out at a point which I'll call positive infinity plus I times epsilon, and I'm moving in towards the origin. Now again, our function is undefined at the origin, so we want to stop some distance from it, which I'll label r here. And then the most natural thing to do here for our integration would be to circle the origin. So I'm going to go around the origin at fixed radius r, and come back out towards infinity. But this is infinity minus I times epsilon. I'm still keeping a distance epsilon away from the positive real line. Now some of you might be wondering, why do I have to integrate on both sides of the real line? Well, remember that when we're doing a contour integration in the complex plane, we have a two-dimensional domain. So the fact that we're integrating above and below the positive real line reflects that fact. Now this contour that we've just drawn here is very important in complex analysis, and it's named after the mathematician who first published on it and demonstrated its importance for the theory of the gamma function. This is called the Hankel contour. So I'll label this contour capital H in honor of Hankel. And we want to study the behavior of the contour integral along H of the function w to z minus 1 times e to the negative w dw, taking the limit as epsilon and r both tend to 0. So I want to draw what that limit contour will look like. I'll lay down another set of coordinate axes, x and I times y. And now we'll draw our branch point and our branch cut along the positive x-axis. And as we let epsilon get really, really small, our contour running parallel to the x-axis gets infinitely close to it. As r becomes infinitely small, the part of the contour that circles the origin becomes infinitely close to the origin without ever touching it. And then the last part of our contour travels back out towards positive infinity, but this time below the positive x-axis at a distance epsilon, which becomes vanishingly small, so that this part of the contour becomes infinitely close to the branch cut from below the x-axis without ever touching. So this is our limit contour, and for the purposes of this video, we'll call this limit contour lowercase h. And so what we'll then be evaluating is the behavior of the function contour integral over lowercase h of the function w to the z minus 1 times e to the negative w dw. And once again, this contour lowercase h is the contour where we're taking the limit as epsilon and r both approach 0. So let me redraw our coordinate axes because we'll need more space here. And I'll label these axes x and I times y. And our goal is to compute the limit contour integral which is the integral over lowercase h of the function w to the z minus 1 times e to the negative w dw. again, as epsilon and r both go to 0. So I'll start by circling our branch point and highlighting our branch cut in red. Okay, this is going to be the domain of integration here. And I'm going to draw the first limb of the Hankel contour, separated some distance epsilon, parallel to the positive x-axis. So we're coming in at infinity plus I epsilon. We're approaching the origin until we get some distance away, which we'll call r. And I'm going to call this part of the Hankel contour capital H sub 1. Now, if we take the limit as epsilon and r both go to 0, this line becomes infinitely close to the x-axis. And so if I were to parametrize this line, this limit contour, our point w on the contour would just become x. Right, the imaginary part of w is going to 0 as I shrink epsilon down to 0. So in the limit, this contour over capital H sub 1 of w to the z minus 1 times e to the negative w dw, in the limit as epsilon and r go to 0, this becomes the limit contour lowercase h sub 1, which is the integral of x to the z minus 1 times e to the negative x dx. So if we want to parametrize the limit contour on this piece of the limit contour, lowercase h sub 1, w just equals x. Now on the piece of the limit contour where we very tightly circle the origin, which I'm going to call lowercase h sub 2, those points can be defined by the equation for a circle in the complex plane. Namely, those points w on the contour will be equal to r times e to the I times theta. And of course, we're going to let r tend to 0, but we'll actually perform that step in the evaluation of the integral in a little bit. So on lowercase h sub 2, the points w are parametrized by the equation w equals r to the e times I theta. And finally, on the outward limb of this limit contour that goes along the x-axis from below, infinitely close to the x-axis from below, the points on that piece of the contour will be parametrized by the equation w equals e to the 2 pi I times x. Now, why do I have that e to the 2 pi I factor there? This is crucially important. This multiplicative factor records the fact that when we went around h2, we went all the way around the origin. So these points that are going along the x-axis from below have a different argument than the ones going along the x-axis from above. These are not the exact same points that we started out with on h1. In fact, we are integrating on the other side of the branch cut. And you may remember that when you multiply a complex number by e to the I times theta, what that means geometrically is you rotate the point representing that complex number around the origin by an angle theta. So that's the fact that we're recording here, and the points along h3 can be parametrized by the equation w equals e to the 2 pi I times x. So now we can write the contour integral along lowercase h, our limit contour, for the function w to the z minus 1 times e to the negative w dw equals, we'll break it up into these pieces, the integral over lowercase h1 of w to the z minus 1 times e to the negative w dw plus the integral over h2 of w to the z minus 1 times e to the negative w dw, plus the integral over h3 of w to the z minus 1 times e to the negative w dw. And now we can substitute in these parameterizations. So over lowercase h1, the integral will be, here I have to be careful, the bounds will be from 0 to infinity. Not from infinity to 0, because I'm actually starting this integration out at positive infinity, journeying in towards the origin and ending at 0. So this will equal the integral from 0 to infinity of the function x to the z minus 1 times e to the negative x dx. dw here just equals dx, obviously, because w equals x. And now we're going to add to this the piece of the contour over h2, where w is parametrized by an equation in theta, r times e to the I theta. So instead of w here, I'm going to substitute in the integral from 2 pi to 0. We end at theta equals 2 pi, and we start at theta equals 0. And instead of w here, I'm writing r times e to the I theta. and I'm raising that whole expression to z minus 1. And this will multiply e to the negative w, but again, w equals r e to the I theta, so this will be e to the negative r times e to the I theta. And then I have this dw term that I have to still work out. Well, if w equals r times e to the I theta, then dw d theta would equal, by the laws of differentiation, I times r times e to the I theta. Therefore, dw just equals I times r times e to the I theta d theta. So let me plug that in for dw there. So this integral looks really ugly, but it actually simplifies fairly quickly. And the last piece of the contour integral is fairly easy. Here w equals e to the 2 pi I times x. So this will be the integral from infinity to 0. Now we're ending at infinity, starting at 0. So e to the 2 pi I times x, all raised to the z minus 1, times e to the negative e to the 2 pi I times x, close parenthesis. And then because on H3 w equals e to the 2 pi I times x, dw equals e to the 2 pi I times dx. So let me move that to the top of the screen here, and now we can make some quick simplifications. First of all, e to the 2 pi I just equals 1, so those terms cancel out and just equal 1 there. And now I want to simplify the second integral we have there, the one where we integrate from 2 pi to 0. In the integrand there, we have r times e to the I theta quantity raised to the z minus 1. Well, that z minus 1 in the exponent can also be written as to the z times, the minus 1 becomes 1 over r times e to the I theta. But then further along at the end, I have this whole expression times I times r times e to the I theta d theta. So I have a 1 over r times e to the I theta, and I have an r times e to the I theta in that integrand. So those terms just cancel, the minus 1 in the exponent and the r times e to the I theta. So now with those simplifications, this expression will equal the integral from 0 to infinity of the function x to the z minus 1 times e to the negative x dx. Well, let me just multiply this integral by negative 1 and exchange those bounds of integration so that I'll have the integral from infinity to 0 instead. And now looking at our second integral, which we already simplified a little, we have an I term there in the integrand, which I'm going to pull out in front. And again, we're taking the limit here as r goes to 0. This is our limit contour. So this will be the limit as r goes to 0 of I times the integral from 2 pi to 0. And now we have, for our r times e to the I theta to the z, I'm just going to write that as r to the z times e to the I times z times theta. And this is going to multiply e to the negative quantity r times e to the I theta d theta. Plus, finally, the integral from infinity to 0 of e to the 2 pi I times z minus 1 times x to the z minus 1 times e to the negative x dx. Now I just want to rearrange these terms slightly. And when we examine the terms in this sum, something really amazing happens. The first term, the negative integral from infinity to 0 of x to the z minus 1 times e to the negative x dx, that just equals negative gamma of z. The second term in the sum, e to the 2 pi I times z minus 1 times the integral from infinity to 0 of x to the z minus 1 times e to the negative x dx, that integral there just equals gamma of z. So let me move this to the top of the screen, and we can factor out gamma of z from those first two terms in the sum, and we get that this sum equals gamma of z times negative 1 plus e to the 2 pi I times z minus 1, close parenthesis, plus this integral that we still need to evaluate, taking the limit as r goes to 0, of I times the integral from 2 pi to 0 of r to the z times e to the I z theta times e to the negative r times e to the I theta, close parenthesis, d theta. So let's consider the limit as r approaches 0 for this integral expression, and we can ignore for the moment the constant factor I that was out in front, since that's not going to affect its limiting behavior. So we have the limit as r approaches 0 of the integral from 0 to 2 pi of the product of terms r to the z, where z is a complex number, times e to the I times z times theta, times e to the negative r times e to the I theta d theta. And again, z is a complex number of the form a plus b times I. And the first fact to keep in mind is the triangle inequality for integrals. So that theorem says that if I take the modulus of a complex integral, so if I take the modulus of this entire integral, I know that that value, that magnitude, must be less than or equal to taking the integral of the modulus of the terms inside the integral. Now, I'm not going to prove this theorem that we're relying on, but if you've never seen it before, hopefully it makes intuitive sense that the magnitude of an integral of a function is always going to be less than or equal to the magnitude of the integral of the absolute value of that function. Now, the next fact that we're going to need is that the absolute value of a product of terms is always going to be equal to the product of the absolute value or modulus of the individual terms in that product. So what I'm writing here is that the integral from 0 to 2 pi of the modulus of the expression r to the z times e to the I z theta times e to the negative r e to the I theta d theta is equal to the integral from 0 to 2 pi of the modulus of r to the z times the modulus of e to the I z theta times the modulus of e to the negative r e to the I theta times the modulus of d theta, which of course is just d theta. And the last fact we'll need is that the modulus of the expression e to the I times x, where x is a real number, equals, by Euler's identity, the modulus of cosine x plus I times the sine of x, which equals, by the definition of the modulus, the square root of cosine squared x plus sine squared x. And then that's a famous trig identity, of course. That expression just equals 1. So the modulus of e to the ix will always equal 1, regardless of what real value we assign to x. So with those facts in mind, we're ready to evaluate this limit. So we have that the modulus or magnitude of the integral from 0 to 2 pi of the expression r to the z times e to the I z theta times e to the negative r e to the I theta d theta must be less than or equal to the integral from 0 to 2 pi of the modulus of that same expression. And as we already saw, the modulus of this integrand is equal to the product of the moduli of the individual terms. So I'm now going to make that very straightforward substitution. So we have then that the modulus of the integral must be less than or equal to the integral from 2 pi of the modulus of r to the z times the modulus of e to the I z theta times the modulus of e to the negative r e to the I theta d theta. And now what I want to do is to determine bounds on each of the terms on the right-hand side in this integral expression. So let's start by considering the last term. We're going to consider the modulus of the expression e to the negative r e to the I theta, remembering, of course, that e to the I theta equals cosine theta plus I sine theta by Euler's identity. So then we have that the modulus of e to the negative r e to the I theta equals, by Euler's identity, the modulus of e to the negative r times the quantity cosine theta plus I sine theta. And then simplifying further, this equals the modulus of e to the negative r cosine theta times e to the I times negative r sine theta. And then once again, because the modulus of a product of terms is equal to the product of the moduli of terms, this will equal the modulus of e to the negative r cosine theta times the modulus of e to the I times negative r sine theta. But the term negative r sine theta is just some real number. So we can call this x, and this is really just e to the ix, and we know that the modulus of e to the ix always equals 1. So we get that the modulus of the expression e to the negative r e to the I theta just equals the modulus of e to the negative r cosine theta. So we've seen that the modulus of e to the negative r times e to the I theta really just boils down to the modulus of e to the negative r cosine theta. Now, theta can vary between 0 and 2 pi, which means that the cosine of theta will be ranging between -1 and +1. But remember from the way that we framed this problem that r has to be a positive number. It's the radius of the contour as we travel around the origin. So we need to take that into account as we look at what the possible maximum of the expression e to the negative r cosine theta would be. We need this maximum again because we want to put a bound on the modulus of e to the negative r cosine theta. Well, this maximum will occur when we're raising e to a positive number, which means we want cosine theta to be negative so that we have negative r times a negative number, which yields a positive number. We also want the term negative r cosine theta, in addition to being positive, to be as large as possible, and that's going to occur at the point where theta equals pi, because cosine of pi equals -1. And so that's where the expression e to the negative r cosine theta is going to attain its maximum, and we're going to have e to the negative r times -1, which of course just equals e to the r. So now we know that the modulus of the expression e to the negative r times e to the I theta can never be greater than e to the r. It's less than or equal to e to the r. Now remember that in this problem we're going to take the limit as r goes to 0. So we can actually make r as small as we want here for this bound. So just for the sake of concreteness, I'm going to set r equal to 1 as the upper boundary for what this radius could equal. And so we're limiting ourselves to consider the possibilities where r is greater than 0 but less than or equal to 1. So then we have for all positive r less than or equal to 1 that the modulus of the expression e to the negative r times e to the I theta must be less than or equal to e to the 1, which of course is just e. And so now we have a bound for our term in the integral, the modulus of e to the negative r times e to the I theta, and that bound is namely the constant e, Euler's number, at least for r greater than 0 and less than or equal to 1. And that's fine here because we're eventually going to consider the limit as r approaches 0. So it's fine that we're limiting ourselves to the consideration of small values of r. So next we want to consider the middle term in this integral, the modulus of e to the iz theta. And here we need to remember that z is a complex number of the form a plus b times I. So we have that the modulus of e to the I times z times theta equals the modulus of e to the I times theta times the quantity a plus bi. And now when I distribute the I across, I have that this equals the modulus of e to the I times theta times a minus, remember that I squared of course is -1, so minus theta times b. And so this will then equal the modulus of e to the I times theta times a times e to the minus theta times b. Now, I can split that into the modulus of e to the I theta a times the modulus of e to the negative theta times b. And now the modulus of e to the I times theta a, well, theta times a is just going to be a real number, which I can relabel as x. This is, again, just a disguised form of e to the ix, and we know the modulus of e to the ix always equals 1. And so we see that the expression modulus of e to the I times z times theta really just reduces down to the expression modulus of e to the negative theta times b. So now we want to find the maximum possible modulus of this expression e to the negative theta b. And because we're raising e to some power, obviously we want negative theta times b to work out to be a positive number. That's going to make e to the negative theta times b as large as possible. How do we do that? Well, we already have that theta ranges between 0 and 2 pi, so to make the expression negative theta times b positive, we need to assume that b is a negative real number. Equivalently, we can make the expression negative theta b always greater than or equal to 0 by just taking its absolute value. So what we're claiming here is that the modulus of the expression e to the I times z times theta must be less than or equal to the modulus of e to the absolute value of theta times b, where again b is the imaginary part of z. But remember, theta ranges between 0 and 2 pi. So if I want to make e to the theta b as large as possible, I would do so by setting theta equal to 2 pi. And then I'll have that the modulus of e to the I z theta must be less than or equal to the modulus of e to the absolute value of 2 pi b. But of course, 2 pi is already positive, so I can just put the absolute value sign around b, and then I have that the modulus of e to the iz theta must be less than or equal to e to the 2 pi times the absolute value of b. So that's our bound on the modulus of our term e to the iz theta in the integral, e to the 2 pi times the absolute value of b. And now we just have to consider the modulus of that first term, the modulus of r to the z. So when we consider the modulus of the expression r to the z, we want to again keep in mind here that r is a real number and z is complex. So this will equal the modulus of r to the expression a plus bi. And that will equal the modulus of r to the a times r to the bi, which equals the modulus of r to the a times the modulus of r to the bi. Now, since r is a positive number, I can take away those absolute value signs and just rewrite this expression as r to the a times the modulus of r to the b times I, but I'm going to write r to the bi a little bit cleverly. I'm going to rewrite it as e to the log of r to the bi, and you'll see why I'm doing that in the next step. Because with that change by the laws of exponents, we have that this expression equals r to the a times the modulus of e to the ib log r. I just bring that exponent down there. And so again, b log r is just some real number that I can relabel x, and we see once again we have in disguised form the modulus of e to the ix, which always equals 1. So we see finally that the expression modulus of r to the z, where z is a complex number, just reduces down to r to the a, where a is equal to the real part of z. So we found that the modulus of r to the z can be no greater than r to the a, where a is the real part of z. In fact, it equals r to the a. So we found upper bounds on all of the terms in the product in this integrand, and so we can then make the argument that the modulus of the integral expression on the left-hand side of the screen must be less than or equal to the integral involving the product of all these upper bounds. So it must be less than or equal to the integral from 0 to 2 pi of r to the a, where a is the real part of z, times e to the 2 pi times the absolute value of b, where b is the imaginary part of z, times the constant e, again assuming that our radius here is a positive number less than or equal to 1, d theta. But now when we look at this integral involving all of these upper bounds, we see that these upper bounds are actually constants with respect to the integration taking place. So they can all be pulled out of the integral. So this integral actually equals r to the a times e to the 2 pi times the absolute value of b times e times the integral from 0 to 2 pi of 1 d theta. Well, that's a really easy integral to do. That's just going to equal theta, evaluated at the endpoints at 2 pi and 0. So this expression will then equal r to the a times e to the 2 pi times the absolute value of b times e times 2 pi. Great. So we're finally in a position where we can take the limit as r approaches 0. So we'll do that on both sides of this expression. We have that the limit as r approaches 0 of the modulus of the integral from 0 to 2 pi of r to the z times e to the iz theta times e to the negative r times e to the I theta d theta is less than or equal to the limit as r approaches 0 of the expression r to the a times e to the 2 pi times the absolute value of b times e times 2 pi. And now if you look at the right-hand side of the inequality, you see that we just have an expression in r, namely r to the a, multiplying a bunch of constant terms. Now the limit as r approaches 0 of r to the a, of course, equals 0, provided that a is a positive number. And the reason I make that stipulation is that if a is negative, then r to the a equals 1 over r to the a, which actually diverges as r becomes really small, because then we have a 1 over 0 type expression. So then we have that on the right-hand side of the inequality, provided that the real part of z, that is to say a, is positive, then the limit as r approaches 0 of r to the a times all those constants must equal 0. And therefore we have proved that the limit as r approaches 0 of the modulus of the integral also must equal 0 by virtue of the fact that the modulus is never negative. Therefore, because the limit as r approaches 0 of the modulus of this integral is less than or equal to 0, it must equal 0. Again, provided that the real part of z, that is to say a, is positive. So putting it all together, what we've shown here is that the contour integral over the limit Hankel contour, which for brevity I've just written as I on the left-hand side here, equals gamma of z times the quantity negative 1 plus e to the 2 pi I times the quantity z minus 1, close parenthesis, plus the limit as r approaches 0 of I times this integral expression that we've just painstakingly evaluated. And we showed that it goes to 0 provided that the real part of z is positive. So let's just remind ourselves what I actually represents. It's the integral over the limit Hankel contour lowercase h of the expression w to the z minus 1 times e to the negative w dw, where w and z are both complex numbers. And then rearranging terms on the right-hand side of the equation, we have that this contour integral equals gamma of z times, open parenthesis, e to the 2 pi I z minus 1, minus 1, close parenthesis. Again, provided that the real part of z is greater than 0. So I'm going to put a box around this. This is a very important identity for us, one of the key results of this video. But we're not even done. We can make this result even prettier. And to do that, I'm going to multiply both sides of this equation by e to the negative pi times I times z minus 1. And the motivation for doing that is to make the term on the right a little bit more symmetric. So if I multiply both sides by e to the negative pi I times z minus 1, I get e to the negative pi I times z minus 1 times the contour integral over little h, the limit contour, of w to the z minus 1 times e to the negative w dw equals gamma of z times, open parenthesis, e to the 2 pi I times z minus 1 minus 1, close parenthesis, times e to the negative pi I times z minus 1. And so the right side of this equation will equal gamma of z times, now multiplying through, e to the pi times I times z minus 1 minus e to the negative pi times I times z minus 1, close parenthesis. And now I just want to switch the order of I and pi in the exponent there for cosmetic reasons more than anything else. And now something truly awesome happens. If you can recall from the definition of the complex sign, we would have sine of pi times z minus 1 equals e to the I pi times z minus 1 minus e to the negative I pi times z minus 1 over 2i. And if this step isn't clear to you, please see my previous video on the complex sine and cosine where I derive that relationship. So that term in the parenthesis on the right-hand side of the equation, namely e to the I pi times z minus 1 minus e to the negative I pi times z minus 1, that term would just equal 2i sine pi z minus 1. So we get that the right-hand side of this equation equals gamma of z times 2i sine pi z minus 1. Now let me move that to the top line there. And now I want to focus on the left-hand side of this equation for a moment. We have e to the negative pi I times z minus 1. But e to the negative pi I just equals negative 1. So we can write, switching the order here, gamma of z times 2i sine pi z minus 1 equals negative 1 to the z minus 1 times the integral over the limit contour of w to the z minus 1 times e to the negative w dw. Well, I'm going to bring that negative 1 to the z minus 1 inside the integral. So this will equal the integral, again over lowercase h, of negative 1 to the z minus 1 times w to the z minus 1 times e to the negative w dw. And then negative 1 to the z minus 1 times w to the z minus 1, that just equals negative w to the z minus 1 times e to the negative w dw. So finally, we can write gamma of z equals, dividing both sides by 2I sine pi z minus 1, gamma of z equals 1 over 2I sine pi z minus 1 times the contour integral over the limit contour lowercase h of the function negative w to the z minus 1 times e to the negative w dw. Again, provided that the real part of z is greater than 0, is positive. So let's put a box around this beautiful formula for the gamma function, but we're not even finished. Because you might remember that the goal of this video is to derive a formula for the gamma function which is valid for all complex numbers. Well, so far so good. We've derived a formula that's valid for complex numbers with real part greater than 0. But we want a formula that's going to work for all complex z. Not just complex numbers z whose real part is greater than 0. So in the remainder of this video, I'm going to show how we do that. So we'll begin by considering our original contour h, the Hankel contour. So let me draw our axes again, and I'll label them x and I times y. And so we have our branch point at the origin and our branch cut along the positive x-axis. So we start out at some point, some distance epsilon from the real line. We start out at the point infinity plus I times epsilon, and we move in towards the origin until we get some distance r away from the origin. Then we circle the origin in the counterclockwise direction, and then we go back out towards the point infinity minus I times epsilon. That's our Hankel contour. Okay? And now we can draw our limit contour as we allow epsilon and r to go to 0. So I'll label the large contour capital H, the Hankel contour, and the limit contour lowercase h. And I claim that the integral over the Hankel contour of the function w to the z minus 1 times e to the negative w dw actually equals the integral over the limit contour of the function w to the z minus 1 times e to the negative w dw. And now to prove this result, I'm going to ask you to recall a really important theorem from complex analysis, namely Cauchy's theorem. And Cauchy's theorem states that if I have a contour in the complex plane and the contour is closed, so it loops back on itself, let's call that contour C. And Cauchy's theorem states that if C is a closed curve, a closed contour, nothing pathological like a fractal, just a rectifiable curve. If C is a closed contour, and there's a function f of z which is analytic or differentiable, both within the region bounded by C and on the contour C, then the contour integral on C of f of z dz equals 0. So let's go back to our illustration of the Hankel contour and the limit contour. And to make use of Cauchy's theorem, I'm going to connect these two contours to make one single large closed contour. So instead of saying that we're going all the way out to infinity plus I times epsilon and infinity minus I times epsilon, I'm going to replace infinity with some fixed value r. And then I'm going to make two vertical pieces to close this contour, to connect the large Hankel contour to the small limit contour. So I'm closing the contour with those two vertical segments, and now I want to look at how we're actually going to move around this contour to do the integral. So we'll start at the top at capital H1, and we're going to move inward from r plus I epsilon in towards the origin. We're then going to circle the origin in a counterclockwise orientation, a positive orientation, and I'll call that piece of the contour capital H sub 2. And then once I get to the bottom limb, capital H3, I'm going to head back out towards capital R minus I epsilon. We'll then move up along this vertical segment that connects us to the limit contour, and now I'm going to travel along the lower limb of this limit contour, which I'll label lowercase h sub 3. But note that we're traveling along this piece of the contour in the opposite direction that we were traveling before. we're also going to circle the origin along lowercase h2 in the opposite direction and come out just above the positive x-axis and move along this piece of the contour which I've called h1, which is above the x-axis where we have our branch cut but infinitely close to it until we come to the point R. And then we'll move up that small vertical piece C1 and we're back to where we started. And I'll label the bottom vertical piece C2. So let's just call this entire closed contour capital C. Now on this closed contour C, the function w to the z minus 1 times e to the negative w is analytic, both on the contour and inside the contour, because the contour is actually excluding the origin and the branch cut. So all the points in the complex plane where this function is either not well defined or not differentiable are excluded from this contour. So we can use Cauchy's theorem. And we can say, by Cauchy's theorem, that the contour integral along this closed contour C of the function w to the z minus 1 times e to the negative w dw, which equals the contour integral along C1 plus H1 plus H2 plus H3 plus C2, now importantly minus H3 because we're traveling along it in the negative direction, minus H2 minus H1 of the function w to the z minus 1 times e to the negative w dw, that closed contour integral equals 0. And the next thing to notice is that the vertical pieces of the contour, C1 and C2, on those pieces, as r goes to infinity, their contribution goes to 0, because the integrand, w to the z minus 1 times e to the negative w, which I can rewrite as w to the z minus 1 over e to the w, that term goes to 0 as r goes to infinity for any fixed z. And to see that, just make use of L'Hopital's rule. As we let r tend towards infinity, the modulus of w grows without bound. So we have an infinity over infinity expression here for w to the z minus 1 over e to the w. If we successively differentiate the numerator and the denominator of that expression, we eventually get a limit equal to 0. So again, as r tends to infinity, the contribution from those two vertical segments of the contour equals 0. So I can cross out those pieces, C1 and C2, and we then have that the contour integral of the function w to the z minus 1 times e to the negative w dw over capital H1 plus capital H2 plus capital H3 minus lowercase h1 minus lowercase h2 minus lowercase h3 equals 0. Well, we can break that expression up into the integral over capital H1 plus the integral over capital H2 plus the integral over capital H3 minus the integral over lowercase h1 minus the integral over lowercase h2 minus the integral over lowercase h3, and again that entire expression just equals 0. But that's just another way of saying that the integral over the Hankel contour minus the integral over the limit contour equals 0. So in other words, the integral over the Hankel contour for the function w to the z minus 1 times e to the negative w dw equals the integral over the limit contour of that same function, QED. Well, why does it matter that those two contour integrals are equal to each other? So this is the answer to the so what question. Well, because we know that the contour integral along our limit contour, here let me just draw the domain again, so here's our coordinate axes, our branch point and branch cut. Because we know that the contour integral around this limit contour that I'm drawing here, the integral over little h for the function w to the z minus 1 times e to the negative w dw equals the contour integral around the Hankel contour, which I'm drawing here. Okay, so this is our Hankel contour. And the contour integral over capital H is again integrating the function w to the z minus 1 times e to the negative w dw. Because those two things are equal, we can multiply them both by negative 1 to the z minus 1. So I'll do that here. I'm multiplying both integrals by negative 1 to the z minus 1. And so then we get that the contour integral over the limit contour of the function negative w to the z minus 1 times e to the negative w dw equals the contour integral over the Hankel contour of that same function. But we already showed that gamma of z equals 1 over 2I sine pi times z minus 1 times the integral over the limit contour over little h of the function negative w to the z minus 1 times e to the negative w dw. Again, provided that the real part of z is greater than 0. So let me move that to the top of the screen here. And now here's the payoff for all that hard work we did using Cauchy's theorem, because we showed that the integral over the limit contour is equal to the integral over the Hankel contour. I can write gamma of z equals 1 over 2I sine pi z minus 1 times the integral over the Hankel contour of the function negative w to the z minus 1 times e to the negative w dw. But here's the wonderful thing. The contour integral over the Hankel contour of the function negative w to the z minus 1 times e to the negative w dw, that integral converges for all z, except where we have poles at 0 and the negative integers. Because remember, we made that stipulation that the real part of z had to be greater than 0 because the piece of the limit contour that diverged, lowercase h2, diverged whenever the real part of z was negative. And it diverged as we made r vanishingly small, as we took the radius down to 0. But we're not doing that on the Hankel contour. On the Hankel contour, on capital H2, we can choose an r as large as we want. So we avoid this issue of divergence on the Hankel contour because we're not taking r down to 0. So we can drop the requirement that the real part of z has to be greater than 0. And what we've done is essentially analytic continuation. We've derived a new definition of gamma of z. And this new definition, in terms of the Hankel contour, actually agrees with our old definition wherever the real part of z is greater than 0. But while our definition of the gamma function in terms of the limit contour was only valid for complex numbers z whose real part was greater than 0, our new definition of the gamma function in terms of the Hankel contour is actually valid for all z except for 0 and the negative integers, where we already know the gamma function has poles. Now, just upon visual inspection of this formula for gamma of z, we can draw a few quick conclusions. Notice that we'll have a 0 in the denominator for 2I sine pi times z minus 1 whenever z is an integer. But we know that gamma of z equals z minus 1 factorial whenever z is a positive integer. That therefore indicates that the contour integral of the function negative w to the z minus 1 times e to the negative w dw must equal 0 whenever z is a positive integer, so that we obtain a 0 over 0 expression for gamma of z wherever z is a positive integer, and that 0 over 0 expression can be evaluated as a limit, which works out to z minus 1 factorial. Furthermore, because we know that gamma of z has poles at z equals 0 and at the negative integers, this contour integral must equal some non-zero constant c whenever z equals 0, negative 1, negative 2, etc., so that we get gamma of z equals some non-zero constant c over 0, which of course diverges, equals infinity, giving us the poles that we already know the gamma function has at z equals 0, negative 1, negative 2, and at all the negative integers. Furthermore, aside from its deep theoretical interest as a formula for the gamma function which is valid for all z, the Hankel contour can provide computational results for determining gamma of z using methods of numerical estimation. And perhaps most importantly for us, the Hankel Contour definition of the gamma function forms the basis for Riemann's first proof of the functional equation of the zeta function, which will be a topic for a future video, which I hope you'll tune in for. So that's it for today. Thank you for watching, and please like or subscribe or leave any comments you'd like on my YouTube channel. Thanks, and hope to see you again soon.